Max Planck is remembered today as the father of quantum theory, one of the most important developments in the history of physics. Yet, what makes his story especially interesting is that he did not set out to revolutionize science. In fact, Planck was deeply committed to the classical physics of the 19th century and was reluctant to abandon it. His breakthrough came not from a desire to create a new theory, but from an effort to solve a stubborn problem that classical physics could not explain. Planck was born in 1858 in Kiel, Germany, into a family with a strong academic tradition. From an early age, he showed an interest in mathematics and physics, but he also possessed a deep appreciation for order and structure. These traits would shape his scientific work. As a young man, Planck entered the University of Munich and later studied in Berlin, where he was influenced by leading physicists of the time. He chose to focus on thermodynamics, the study of heat and energy, which was considered a well-established and nearly complete field. By the late 19th century, many physicists believed that the major problems of physics had already been solved. The laws of motion developed by Newton, combined with Maxwell's theory of electromagnetism, seemed to explain the natural world with remarkable accuracy. Only a few minor details remained unresolved, or so it seemed. One of those minor details turned out to be anything but minor. It involved the study of blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and re-emits energy based solely on its temperature. Physicists could measure this radiation very precisely in the laboratory, but they struggled to explain the results using classical theory. The problem became especially severe at short wavelengths, in the ultraviolet region of the spectrum. Classical physics predicted that a heated object should emit an infinite amount of energy at these wavelengths. This result was clearly impossible and did not match experimental observations. The discrepancy became known as the ultraviolet catastrophe. Planck was drawn to this problem around the year 1900. His goal was not to overturn classical physics, but to find a mathematical formula that matched the experimental data. After considerable effort, he succeeded in deriving an equation that fit the observed spectrum perfectly. However, there was a catch. To make the math work, Planck had to introduce an assumption that went against everything classical physics stood for. He proposed that energy is not emitted continuously, but rather in small discrete packets. These packets would later be called quanta. According to Planck, the energy of each packet is proportional to the frequency of the radiation, given by the relation E equals h times f, where h is a constant now known as Planck's constant. This idea was revolutionary. In classical physics, energy could take on any value, increasing or decreasing smoothly. Planck's proposal suggested that energy comes in fixed units, like steps on a staircase rather than a smooth ramp. At first, Planck himself did not fully believe the physical reality of this idea. He viewed it as a mathematical trick, a convenient way to match theory with experiment. Nevertheless, the result was correct, and it marked the beginning of a new era in physics. The full significance of Planck's work was not immediately recognized. It would take the contributions of other scientists to develop the concept further. In 1905, Albert Einstein used the idea of energy quanta to explain the photoelectric effect, showing that light itself behaves as if it is made of particles, later called photons. Over the next few decades, physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger expanded these ideas into a complete theory of quantum mechanics. Planck lived to see these developments, though they challenged many of his original beliefs. He remained cautious about the more radical interpretations of quantum theory, particularly those involving probability and uncertainty. Even so, his initial insight laid the foundation for all that followed. It is important to understand just how significant this shift was. Classical physics describes a world that is predictable and continuous. Quantum theory, by contrast, reveals a world that is discrete and, in many cases, inherently uncertain. This new framework would go on to explain the behavior of atoms, the structure of matter, and the interactions of light and energy at the smallest scales. Today, quantum theory is not just a theoretical construct. It underpins much of modern technology, including semiconductors, lasers, and even the devices we use to watch videos like this one. All of this can be traced back to Planck's decision to introduce a small constant and a bold assumption in order to solve a problem that others could not. Planck received the Nobel Prize in Physics in 1918 for his discovery of energy quanta. Despite this recognition, he remained a modest and thoughtful scientist throughout his life. He continued his work in physics and contributed to the scientific community in Germany during a period of great political and social upheaval. Max Planck passed away in 1947, but his legacy remains firmly established. What began as an attempt to preserve classical physics ultimately led to its transformation. His work opened the door to a deeper understanding of the universe, one that continues to evolve even today. The story of Max Planck reminds us that major breakthroughs do not always come from bold predictions or radical ideas. Sometimes they arise from careful work, persistence, and a willingness to follow the evidence, even when it leads in unexpected directions. Thank you for watching, and I hope you found this look at Max Planck and the origins of quantum theory both clear and informative. If you enjoy content like this, be sure to check out the rest of the channel for more videos on the history of science, physics, and astronomy.